So how do we know when and where we should use technologies like this one in this category, or when another option would be better? I asked an expert for her opinion on this very topic. Dr. Roberta Hofman-Caris has been working on organic micropollutants for over 15 years. She's a senior research scientist at KWR Water Research Institute in the Netherlands and an associate professor at the University of Applied Sciences in Utrecht. Here's what she had to say. The first question I have for you is, how do we know whether the quality of a particular surface water body is affected by pharmaceuticals?
Well, in general, we know that it is affected because we know that, for example, wastewater treatment plants are discharging onto the surface water. And especially in the Netherlands, where the surface water has already passed so many countries with so many wastewater treatment plants, we know that it is present. But we also analyze the water because of the Water Framework Directive to check the quality. And mostly because we use the water as a source for drinking water, then you also have to know what's present.
Okay, and if the lake or the river water is being used for drinking water supplies, then how does the water need to be treated? How does it differ compared with conventional potable water treatment?
For conventional water treatment, in general, you use coagulation, flocculation, sedimentation, followed by dissolved air filtration or rapid sand filtration. And that should be sufficient. But in that way, you cannot remove organic micropollutants like pharmaceuticals. In that case, we have three possibilities in general. You could either remove it from water by using a membrane. You could also remove it by adsorption. General activated carbon is used for that. And the third option is that you really destroy the compounds by applying some kind of oxidation process. And there's a range of oxidation processes and advanced oxidation processes that can be applied for them.
How do you choose which technology to use? Can you predict the effectiveness of a particular treatment technology?
Yes, at the moment we can. I can say we can. We've been working in the past decade, I think, at KWR to find a way to predict the removal of organic micropollutants by certain techniques. And we base those techniques on the molecular properties of the contaminants. So by using quantitative structure property analysis, relationships, QSPRs, we can make a statistic relation between certain parameters, like the permeability of a membrane for that compound, or its adsorption behavior, or how it can be oxidized, the oxidation rate constants, the quantum yield if photolysis is applied. We can relate those properties to the molecular characteristics of the compounds. And this can be fed into models that predict what will happen to the organic micropollutant during a certain process. And in this way, we can already predict which kind of technology may be effective. And that means that we can reduce the costs of testing.
That sounds like it would work really well where there are not too many interfering compounds in the water, so good for pure water. What if there's competition from something like natural organic matter, or how does that work with wastewater, which must be much more complicated?
The matrix of wastewater is more complicated than the matrix of surface water. Although, of course, surface water consists partly of effluent from a wastewater treatment plant. So we can manage with our models quite well. But what you sometimes see is that it's not the modeling that causes the trouble. That if you want to treat wastewater, but that you first have to do a pre-treatment to improve water quality. For example, to improve the UV transmission of the water, or to remove some of the reactive organic compounds that are present in natural organic compounds. So maybe it's not that we cannot use the models, but it's more that we need a pre-treatment to make the process more effective.
And is that true for all wastewaters in general, or more for specific types of wastewaters, like hospital waste, for example, that you would expect to carry a higher load?
Well, partly. The wastewater from hospitals carries a higher load, but in general, it contributes for less than 10% to the total pharmaceutical load of surface water, because most of it comes from the communities, from the houses where people live, because they are using the medicines at home. And so more than 90% comes from the municipalities, from the towns and villages where people live. So that's not the biggest problem. On the other hand, hospital wastewater has a different composition. And we are also working on local decentralized treatment of hospital wastewater, for example, to treat that water before it enters the surface water. One of the reasons also is that you have different problems with hospital wastewater. For example, in antibiotic resistant genes. And in hospitals, antibiotics are used as a last resort. And we certainly don't want resistance to occur for those antibiotics, because that would really be a disaster.
Thank you so much, Roberta. Roberta's group has published some landmark work on monitoring and modelling the fate of micropollutants, including pharmaceuticals, in the environment.